Okay, hello everyone. Hello to the people listening to this recording. I didn't check if I'm recording audio, so I'll do it now. And I'll interrupt this. Yeah, audio is on. Okay, no mess-ups like last time. Okay, so what we're going to speak about today is algorithms, complexity, and efficiency of data structures. Okay, a warning before that, this is a bit too theoretical. Don't try to think too much about how this stuff works. Just take it as proven and don't try to analyze everything. Algorithms complexity is a very large subject and something that you could study in university, I think. And it involves a lot of math and a lot of other stuff. We'll just learn some basics so you can calculate how fast your program works and calculate if you have a time limit error before you even submit your task at your exam. Okay, so we'll talk about what the heck is algorithm complexity, why do we need that, why don't we just measure time, for example, calculation speed, etc. More importantly, we'll talk about this thing. Choosing the appropriate data structure for your algorithm, meaning that not every data structure, as you've already seen, is applicable and is good for your algorithm. There are some data structures good for some stuff, other ones good for other stuff. That's why we have a lot of data structures, actually. Okay, not just because they're hard to implement. Okay, moving on. We'll talk, first we'll grasp a little bit the math stuff. What do I mean by that? We'll talk about a thing called asymptotic notation. We'll talk about what is complexity considering time and considering memory. We'll talk about, of course, mean, average, and worst cases. So what's that? Well, normally when you write a program, you want to know how fast it works. You want to do a basic calculation on how stuff works at the basic level. Roughly how fast it will go on different PCs. Well, how do you do that? Well, you generally base your assumptions on how much data you have to process. For example, if you have an array, some sort of array, and you have to find the minimal element of that array. And what do? Well, you go through all the elements, and in the best case, not searching the minimum element, searching for some element. For example, we're searching for the element with value 6. And in the best case, the element with value 6 will be at position 1st. And your algorithm breaks its operation right over here. You do one operation. In the worst case, however, 6 could be over here. And that means you have to go through all of the elements. That means that if you have n elements in your array, this is n, you have to do n steps. That's basically calculating your complexity. Generally, when we calculate complexity of algorithms, we'll always talk about worst case. We'll always be pessimists. We'll always consider what will happen if we have our worst case here. If we have the worst possible data input to our algorithm, how fast will it work? That's what matters. There's another thing called average case, which takes the best case and the worst case and computes the average of those two. Meaning that for the average case of searching an element in an array is n divided by 2. Why? Because the best case is the element is at first position, the worst case is the element is at last position. Do the average of those and you get the answer. Okay, but we'll speak mostly about how we calculate complexity in worst cases. Meaning that you have some input data, it's as large as possible, as large as your constraints can offer you, and it's as evil as possible so it can crash your algorithm. So, then we'll go through comparing some of the data structures you've learned by now, and the abstract data types also. I'm talking about arrays, lists, trees, and hash tables. We'll see the benefits of using trees, for example, versus hash tables. We'll see the benefits on the counter case. We'll see everything we could see. We'll give you some statistics and etc. Okay, and you'll learn how to choose your proper data structure. We've spoken about this stuff earlier when we spoke about the data structures themselves, but now we'll sum it up in one big lecture. Okay, you know, you can't make a program without having a data structure and some algorithm, some sequence of steps. Whoa, what happened? Some sequence of steps which have to be, which have to be executed. Normally, when you began learning programming, you just had to do a sequence of steps. Then you started learning that you need to store those sequences of steps. For example, you need to calculate the sequence of Fibonacci, and then not just calculate it, but for example, take the fifth element, the sixth element, give the answer to the question, what is the value of the nth element of the Fibonacci sequence, and do that 1,000,000 times. And then you learn that you need to use an array, so it's fast. So basically in programming, you'll use a lot of algorithms and a lot of data types. You already know that. And it's essential to know, not to implement those data types, but to know which one is best. All of these things are already provided. Linked list, stack, queue, hash table, dictionaries, and etc. Sorted sets. All of those things are provided, and even if they aren't provided in .NET, you could find them in some other place. For example, WinTelect's Power Collection. You can go and search for them there. So it's not that important to know how to program them, because it's hard, and in the general case, you will have some access to them. It's more important to know which one is better in which situation. And calculating how fast your algorithm works is the basis of all programming. You can't make an algorithm that calculates Fibonacci 10 hours. It's unacceptable. Well, unless you calculate Fibonacci for the 1,000,000th element or something like that. But generally, making programs which work fast is what you need to do, so you will have success in the IT industry. No user will buy a program that works slow, even if they have a very powerful computer. They will always choose the lighter version. Okay, so more about the math behind this stuff. How do you analyze algorithms? Generally, I told you that the idea is to take into account the amount of data you have to process. You always have some data to process. You have an array, you have a tree or something like that. You have something you have to read. You have a text, you have a picture, it doesn't matter, something. Some amount of information. You have to calculate how much information you have and how much times you need to go through it. That's the basics of analyzing an algorithm. The primary things you need to consider is, first of all, time. The speed at which you do calculations and give answers to questions, to queries, is the most important thing. After that, it's memory space, RAM memory. Why after that? Well, because RAM memory is cheap. It's generally cheap, and for now it's not that important to take up very little RAM. We have a lot of RAM now, a lot of memory, and we can take up, well, not as much as we want, but close to that. But everyone's short on time, so you have to calculate your time. In the general case, you will prefer time over RAM. There are other stuff, for example, bandwidth, meaning that, for example, your processor works very fast, but it transmits that information relatively slow to the other parts. Things like that are also considered when you analyze algorithm complexity, but we won't bother with that right now. We could analyze that at later moments. Okay, how do you calculate time? You can't just say, okay, I made this algorithm and it works for 5 seconds on my PC. What does that mean? Your PC could be 3 GHz and my PC, my processor, could be 1 GHz. And that would mean that it would run 15 seconds at my computer. Okay, so analyzing algorithms is done by analyzing the number of steps they do. We don't care exactly about the time they work. That time depends on the processor, the central processor which is working on our program. What we need to know is how fast, not how fast, but how many steps that processor will have to do. And that is calculatable for any type of processor. You don't need to know what processor you're using to calculate how many primitive steps, and that's what primitive operations or primitive steps, that's the term we'll be using from now on. What is a primitive step? Well, it could be a lot of things, but generally the amount of data which a processor can process at one step, at one of its cycles or operations. Again, it depends on how you define your step for your algorithm. Your step could be 10 operations, it could be 20 operations. But it's the number of things, the thing you do for all the data, that's a primitive operation. For example, you do a for loop and you print the current element of the array. That's a primitive operation. Printing the current element is a primitive operation in the entire algorithm which goes through all of the elements and prints all of them. Or, for example, calculating the nth number of the Fibonacci sequence. Well, a primitive operation in that algorithm would be summing the n-1th and n-2nd element of the sequence and obtaining the nth. So primitive operations is something you could change the meaning of. You just need to know how many things, basically the thing you have in your loop. A more practical example, the thing you have in your loop's body, that's a primitive operation. The times you do that is the complexity of your algorithm. Okay, so yeah, algorithm complexity will call how many times we do the things in our loops. How many times do our loops repeat? Okay, what does that measure? Well, I told you that you won't be needing to measure this. CPU time will be different on each and every processor. You will have to calculate that for each and every processor. You won't do that. But when you have the number of steps, for example, you know that you have input data with the size of n, where n is, for example, 60. And you have some 60 elements, and your complexity is, for example, 2 times n. We'll talk about what that means exactly later on. Basically, what it means is that for 60 elements, you will have to do a total of 120 operations. Okay, what do you then do then? Well, you calculate how much time one operation costs for the PC you're running it on, and you just multiply by that. Multiply, for example, by 7 or something like that. And you receive a number, and that will be the time which the processor will work. That's a very, very basic example. What you actually need to get is this thing. How many times does the primitive operation have to be executed? After you get that, you're basically platforming in specific. And when you need to calculate the exact number, you just get this thing and calculate it when you need it. Our target, our purpose here is to learn how to calculate this 2 times n, n at the power of 2, etc., etc., etc. Logarithm of n, and so on. Other things you'll measure, memory. Memory is measured quite easily compared to CPU time. Memory is always memory. In CPU time, you don't know how fast it will go. Memory, well, you always know that if you take up 120 megabytes, well, you'll take up 120 megabytes. You can't change that. But processor time changes on different processors. Okay. So, what I told you already, you calculate the number of steps. Only then. Nothing more than that. After you've calculated that, well, if you really need to know how fast it will run, well, then calculate that according to your processor on which you're running it. But this is the most important thing. Not more than that. Okay. Other particular operations can also be calculated. Actually, algorithm analysis is something very deep, and it works even on disk operations. It works on a lot of stuff. That's why we have B trees, by the way. If you remember the B tree is especially designed to work fast on hardware. It's made so it's efficient on hardware, not just algorithmically. So algorithm analysis and algorithm complexity covers even that. We, for now, won't care about this stuff. We'll care only about this and this thing over here, asymptotic complexity. We'll mention what that means in just a moment. Okay, moving on. I told you about worst case, average case, and best case. What we'll care about the most is worst case behavior. When we have the worst possible data that can occur. When we're screwed up as much as possible, basically. When you see a task and you have constraints of 1 million for all of the numbers, worst case means that all of the numbers will be 1 million. That's worst case. And you should always calculate for worst case. Always prepare for the worst. That's basically the slogan of analyzing algorithms. Okay. Average case. You need average case basically to understand what happens with your algorithm generally. If you calculate the average case running time of your algorithm, the average case running steps, you will know that for 1 million executions, for example, 80% of them will run in average case, because it's average case. But average case is not always trivial to calculate, and it's basically wishful thinking. You shouldn't do wishful thinking when you're making your algorithms. You shouldn't depend on that. So you always calculate worst case. That's the best pre-assurance. You prepare for the worst. You make your algorithm work the best at the worst cases, and it will work good on these also. Okay. So I told you an example of worst case comparisons, worst case complexity. You have to search through an array, and you're looking for the element with value 6, and worst case means 6 is over here at the last position, or 7 or something like that. You're searching for 7, 7 is the last place, you have to go through all of the elements. Best case, well, 7 is over here. Average case, well, 7 is somewhere around here, in the middle. And average case, as a rule, is computed by worst case plus average case plus best case divided by 2. That's the general value of the average case. Again, you won't need to care about that too much. Here we'll mention our first term, and it will be linear time. What is linear time? Well, linear time means you have an input stream of n elements. You have n elements. When you have n elements, linear time means going through those things independently of how much they are. What does that mean? Well, linear time is basically, you've all seen linear equations. What does a linear equation look like? Well, you have, for example, 5 times n plus 1, or 5 times n plus 2, or just n, or something like that. That's a linear equation, a linear polynomial. Well, linear time means you actually run in time dependent only on n, eventually multiplied by some number. For example, you do 3 things for each n, and that will be linear time of 3 times n. Linear time is almost the best case you can run into. There is one better case, we'll talk about it later. A linear number of operations. Linear means it depends on the data you consume only once. We'll see what only once means in just a moment. There's a such thing called the big O notation, or the asymptotic notation, or whatever. That's how you calculate algorithm complexity. Whenever you see this thing, whenever you see O of something, of some function, this is a function over here. Whenever you see something of some function, it means, when you see O of some function, it means the algorithmic complexity of that function. Basically, that will be what you need to know. It's actually called asymptotic notation, and it does some tricky math stuff. It's not important how it does it, it's important what it gives you. This thing gives you how fast your algorithm works, mathematically. You don't have a built-in function for that. So, this is basing your calculations about how fast your algorithm will run exactly on the data stream. This is the data stream, for example. This is a function of the data stream. That function of the data stream could be operate on the data stream 3 times, or go through each of the elements in the data stream once, or go through a part of the data stream in some way. So basically, this is what you do with your data, and this is how fast it will go, the entire thing. Okay, so linear complexity of this thing means if you have, for example, a number of elements which is n in your data stream, then if you have linear complexity, then you have the big O notation of n. That's linear complexity, and G will be n in this case, in linear complexity. Quadratic complexity or cubic complexity and so on will be, for example, for quadratic complexity, what do you have? Well, you have n at the power of 2. That means each element of those n elements is processed the number of times equal to the number of elements. A little more clearly, you have n elements, and you have, okay, these are the elements. Each of these elements is processed exactly n times. That's quadratic complexity. You do, for this element, you do n operations. Then for this element, again, n operations, and so on, and so on, and so on. Okay, so basically, what you need to remember from here, aside from all the math stuff, is big O of something denotes how fast that algorithm will work. This thing is almost the best case. A linear algorithm complexity means the number of elements you have, that's the speed at which you run. If you have algorithm complexity of n at the power of 2, that will be much slower. The more data you have, the slower and slower your algorithm will run. Meaning that in this case, you have 10 elements, your algorithm will run 10 times slower than when you have 1 element. Okay, so doing a basic comparison. If you have O of n, and n is, for example, 1, this thing is 1, you have 1 operation. If you have big O of n and n is 10, this thing is 10, you have 10 operations. Maybe I should write here. We do this, and then do this. Okay, so we have a big O notation of n elements. And we know that the first time, and the n will be 1. Okay, so the number of operations is 1. Then, n is 10, for example. Here n is 10. Whoa. Okay, not very good at writing on this stuff. When n is 10, like this, you have exactly 10 steps. Okay, if you have quadratic complexity, if you have 1 element, again, where n is 1, this n is 1, you have again 1 step. So far so good. If you have, this is n at the power of 2. If you have, however, quadratic complexity of 10 elements, it will no longer be just a total complexity of 10, it will be 100. So you see that in quadratic complexity, the larger data we have, the slower and slower our algorithm will run. Basically, linear and quadratic and whatever means how fast your algorithm starts running slower and slower. That's probably not the best explanation. Quadratic means if you have some data, your algorithm slows up even slower and even slower with the more data you have. Okay, these things will get a little more clear when we move on. What's asymptotic complexity and asymptotic upper bound. Now, you don't need to remember this. Don't remember this. It will damage your brains. This is something that you could probably learn in university or somewhere else. What does this mean? What you need to remember is, you've all heard of a limit of a function, right? How many of you have heard of a limit of a function? This thing. Okay, a lot of you. In Bulgarian we call it lim s of the function f of n, where n goes to infinity, for example. Okay. When you calculate limits, which will be the same way you calculate algorithm complexity, n is the most important thing. And having such things, for example, like 5n, if you have 5 times n operations, what does that mean? Well, for n which is 1 or 2 or 3, it matters, because 5 times 1 is 5, and 1 is very different than 5, and 5 times 2 is 10, and 2 is very different than 10. Okay, but for 20 million or 100 million, 100 million for us is not much different than 500 million. What I'm trying to say is, when you have algorithm complexity and you have some constants in that complexity, as we said, the algorithm complexity, if this is the data you get in, the function of this, for example, this times 2, not times 2, but at the power of 2, will means multiply the number of elements you have, and you get how slow your program will work. So, if we have this thing, if we have 3 times n at the power of 2, 3 is not important. Why? Well, because n at the power of 2 is something very, very large. Always think of n as a very large number. Then n at the power of 2 will be an even larger number. And big deal, we multiplied it by 3. So what? It changed 3 times, but it's already 1 bazillion million, don't know what that number is, large. So what you need to remember when you're calculating algorithm complexity, you only care about n. Not about if you have 5 times n or 10 times n. Okay, 10 times n could be a problem. But 5 times n, 2 times n, or even the weaker stuff. If you have n plus 2. Come on. If you have, why am I not writing with this function? If you have n plus 2. 2 doesn't matter at all. The larger n becomes, the less valuable 2 becomes. You don't care about 1 million and 1 million and 2. If you get $1 million as a pay raise, you won't mind getting $2 less, for example. It's not that big of a deal. Or if you're getting $10 billion, you won't care if they're 2 times by $10 million or 3 times by $10 million. $10 million. They're still about $10 million. And even larger and larger and larger. I'm starting to twist my tongue too much. Okay, so when you think about algorithm complexity, always think about n as something infinitely large. When you have an infinitely large n, you don't care about 3 times of infinity, or 5 times infinity, or infinity plus 2. Big deal, it's still infinity. But you care about infinity at the power of 2, and infinity divided by some other infinity, or something like that. So basically, what this whole thing over here says is, if you have complexity calculated by this formula, 3 times n at the power of 2 plus n divided by 2 plus 12. What matters from this entire thing is n at the power of 2. Why? Well, because it's the largest thing. In our entire equation, n at the power of 2 is larger than everything else. It's larger than n divided by 2. It's larger than 12. And when n at the power of 2 is something approaching infinity, these things don't matter. These things are close to 0. when comparing to n at the power of 2. And this thing 3 times over here, well, we don't care about it too much. It's 3 times, big deal, 3 times infinity. We don't care about that. So whenever you calculate algorithm complexity, you take into account mainly n. You care about mainly n. It's not that big of a deal if it's 3 times or 10 times n. You care about n. You care about whether it is n at the power of 2, n at the power of 3, n at the power of 5, or something even worse, 2 at the power of n, that's even larger. We'll talk about that later. You care about that. Okay, in this example over here, you have 4 times multiplied by logarithm with the base of 2 of something, and something else. Okay, what do you care about here? Again, we have some stuff, but this time it's not that clear. For example, we have this thing. N multiplied by something, and which of these things here can we take out? 4, big deal, don't care about 4. Okay, logarithm of something. Okay, logarithm of something could mean something. What's that something? Well, we have 3, we don't care about 3. We don't care about 1, but we have n. We care about n. So we have n here, and we have n in our logarithm. So this thing stays, without the 3's and the 1's and the other numbers. Every constant which you have here, you don't care about that much. Okay, this is 2 times n, big deal. It's not as big as n multiplied by something which uses n. So another rule, if you have n multiplied by something which uses n, even if it's not exactly n, so this is almost like n at the power of 2, but it's n multiplied by some other n, by a smaller n, but it's still multiplied by n. So this thing is larger. This is almost like n at the power of 2, because this thing, when it approaches infinity, this thing will be almost n. Not exactly the best explanation, but just consider everywhere where you have n, it's larger. Here you have 2 times. Here you have n at 2 places. 1 place, a second place. Okay, so here you have n only 1 time. Then this thing over here is not important, because this has n 2 times. This thing has n 2 times also. It has n multiplied by n, and so on and so on. So the idea is, those things matter, but they don't matter too much. And we always say that such a complexity belongs to the family of complexities, which is this. Big O notation of n multiplied by logarithm of n. Why? Well, because we used only this. The other stuff, it has some impact when we have smaller numbers. But what's the most important is what happens when we have large numbers. When we have large numbers, we take the largest thing over here. And that's this. Okay. So, moving on. Some typical complexities you could encounter. Enough with the theoretical stuff. Constant complexity. You write this. O of 1. Why of 1? Well, because it's of 1. This means constant complexity. This means I could have 1 million elements. I could have 10,000 elements. I could have 1 billion elements. It doesn't matter. The operation always completes in constant time. You already know of a data structure which works in constant time. What is it? Hash table, yeah. The hash table works in constant time. It doesn't care how much elements you have. It just does some operation independently of those elements. Okay, so you could have 1 million elements, but it will still be 1 or 2 steps. Calculate the hash code and get the value. It doesn't care how many elements you have. Okay, logarithmic complexity. This time you depend on n in some way. How do you depend on n? Logarithm of n. If you have 1 million elements, how much is that? Logarithm of n. Logarithm of 1 million is what? 20, yes. Because 1 million elements is 1 megabyte, and 1 megabyte is generally 2 at the power of 20, something like that. Okay. So logarithm of 1 million elements means 20 or 30 operations. I'm not sure if, oh, that's 1 billion operations. So if this thing was 1 million, this would be, oops. If this thing was if this thing was 1 million, this would be 20 operations. For 1 billion, as it is now, it's 30 operations, and so on and so on. Okay, so that's logarithmic complexity. You have 100 elements. For 100 elements, you will have logarithm of 100, which is what? 5, 6, 7. 7 operations for 100 elements. That's logarithmic complexity. But you do depend on n. When n becomes larger, your operations become more. Okay. Linear complexity, you have 100 elements, you do 100 operations. Basically, that's what it means. Okay. Moving on. Oh, not only the case where you have n operations. If you have 100 operations and 100 elements and you do 50 operations, that's still linear complexity. Why? Well, because getting 50 from 100 is division by 2, right? And that's a linear operation. It's not square root. If we have 10 operations of 100, well, that's not very clear. It could be square root. It could be division by 10. You need another set of samples. For example, if you have for 100 elements 10 operations and for 10,000 elements 100 operations, that's some sort of quadratic complexity, because 100 operations for 1,000 operations, that's exactly the square root of 1,000. So your complexity in this case would be square root of n. And I'm not sure how you can achieve that, but it could be possible. If you, however, have 1,000 operations for 10,000 operations, for 10,000 data parts, and 10 operations for 100 data parts, that's linear complexity. Why? Well, because 100 divided by 10 is 10, and 1,000 divided by 10 is 10,000 divided by 10 is 1,000. So that's a linear equation. Basically, you try to guess what your equation is. Okay, quadratic equations. For each element, you go through all of the other elements, for example. If you want to create all of the pairs in one array, for example, you have an array of n elements. These are some elements. This is n. All of the elements are n. And you want to create all of the pairs. For example, you want to create this. These are some cities. And in the last lecture, we had link, and we had an example which went through all cities and made all possible pairs. And it said, for example, Sofia, Sofia, Sofia Burgas, Sofia Varna, Sofia Constantinople, and etc. and so on. Okay, so that's quadratic complexity. Because for each element, you go through all of the other elements. And if you have 500 elements, well, 500 at the power of 2 is, what's that, 250,000 operations. You can calculate that. If you have 10 elements, well, 10 at the power of 2 is 100 operations, and so on. That's quadratic complexity. Cubic complexity, well, same thing, only you raise to the power of 3. And this thing grows very fast, and the things after that grow even faster. You could have hypercubic complexity, which is n at the power of 4. You could have something like that. What's very scary, however, is exponential complexity. What does exponential complexity mean? Well, if you have a program working with exponential complexity, you're basically screwed. Very screwed. That thing, why are you screwed? Okay, this thing grows very, very faster than n at the power of 3. If you have n at the power of 3, you're still okay. But if you have 3 at the power of n, that's very, very bad. Because that thing grows very, very fast. How do you prove that? Well, a simple example would be normal complexities include this thing, right? Logarithm of n. What does the function of logarithm of n look like? If we have these coordinate axes. Okay. How does logarithm of n look like? Well, if this is n over here, and this is logarithm of n over here, how does this thing look like? Well, it basically looks like this. It goes like this, and this, and this, and this, and this. And the larger n becomes, the slower this thing grows, because it's logarithm. That's how it works. Logarithm, you've all seen logarithm of n. This is logarithm of n. And this thing grows slowly, relatively slowly. That can be proven mathematically, but that's how its function looks like. This is how, a good color, this is how 2 at the power of n looks like. It looks like this. Look at the curve. The curve is in a different direction. This curve is like this. I should have used the other color. This curve is like this. So basically, the larger n becomes, the faster it grows. 2 at the power of n grows much faster than logarithm of n, or n at the power of 3. Because here you have a constant power. This power is 3. It's always 3. It's like multiplying by 3. It's always multiplying by 3. It's not like multiplying by n. Well, here you have the same thing. A number, however, at the power of n, and n grows. And the faster n grows, the faster this number will grow. This means that basically you're making your growth dependent on your data stream. And if your data stream is very large, your operations will grow much faster. That means you will do a much larger amount of operations. Not to speak about k at the power of n. This is one number that could go to infinity, and another number that could again go to infinity. So that's infinity at the power of infinity. That's even worse. Okay. And n factorial, or not very sure how that's pronounced, this thing grows even faster. These 3 things, and also 3 at the power of n, or 15 at the power of n, these things grow very fast. You should try to avoid them. Okay. So, this thing, you don't need to learn it by heart. That thing you could derive it yourself. Why? Well, constant complexity, it doesn't depend on the data stream. This up over here is the data stream. This thing is the data stream. The number of elements in the stream, it's always, for example, 1 second or something like that. Okay, this thing, it relatively depends on the data stream, but it's still very small. Logarithm of n is still something very small. For 100,000, it's what? Not 32, it's 16 or 17 or something like that. Okay. When you go to this exponential stuff, it will hang. Meaning, if you have n at the power of n, this thing will be very, very, very slow. It will kill your computer. So, generally what programmers do, well, they try to avoid this kind of complexity. If you have this kind of complexity, you need an ASA computer. Okay, moving on. Time and memory, let's see, where are we? Okay. A little more and we'll have a break. Okay, so, complexity, up until now we used only one variable, we just used n. If you have different data streams, for example, you have a graph. And in a graph, what do you have? Well, we have edges and vertices. And you have a number of edges, which is n, and a number of vertices, which is m. So for a graph, you actually have 2 things which control your speed of operations. You have n multiplied by m, or summed by m, depending on your traversing algorithm. Okay, so basically doing a DFS or a BFS traversal will cost you n plus m time. And this thing matters. Why? Well, because n is infinity, for example, and m again is infinity. So 2 things which could be infinity, but different infinities, summed together means something. But 2 of the same stuff doesn't mean anything. Okay. One other thing that's important, you could have 3 variables here, or 10 variables, or whatever, depending on how your algorithm functions. DFS uses two things, edges and vertices. So it will have two things. Searching for the smallest element in an array just uses the elements in the array, one thing. So it will have one variable as a parameter. Okay, so what you should also calculate at some situations, you should calculate what memory you're using. In some cases you use a lot of memory and you'll go out of the bounds of your RAM and you'll get an out of memory exception. When can you get that? Well, if you have a memory complexity is calculated the same way as time complexity. If you have memory complexity and that memory complexity is, for example, n at the power of 2 or at the power of 3, for 50,000 elements, if you duplicate those elements n times, what do? Well, 50,000 multiplied by 50,000. We turn on the calculator, not Call of Duty. We turn on the calculator and we do 50,000 multiplied by 50,000. And that divided by 1 million is 2,500 megabytes. So that's 2.5 gigabytes. So my computer won't crash at 50,000. But if it's 60,000 or something a little larger, it will crash. So sometimes you will need to calculate memory consumption. But it will be relatively rare. You will most commonly need to calculate time complexity. How do you calculate memory complexity? Well, if you have to duplicate something. For example, one way of representing graphs, this is a graph, we learned that one way of representing graphs is using a so-called matrix of adjacency. What is a matrix of adjacency? We will have, this is 1, this is 2, this is 3, this is 4. These are the vertices of our graph. And we have 1, 2, 3, 4 over here. 1, 2, 3, 4 over here. And here we have again 1, 2, 3, 4. You all know what a matrix of adjacency is. So this is some matrix. This is one. Yeah, this is nothing. 1, 2, 3, 4, etc., etc., etc. This thing has exactly n at the power of 2 elements, right? Because it has n rows, 4 rows, and 4 columns. 4 by 4 means 16. 4 at the power of 2 is 16. So this thing uses n at the power of 2 memory. So if you have a graph with 50,000 vertices, this will use the memory of one vertex, the memory used for one vertex, multiplied by 50,000 at the power of 2. The memory for one vertex will most probably be at least an integer, or okay, a bool. If it's a bool, that's 1 byte. 1 byte multiplied by 2.5 is exactly 2.5 gigabytes. Just for storing 50,000 elements. There are more than 50,000 cities on Earth, and if Google used an adjacency matrix, it would use 2.5 gigabytes. I'm not sure they could use. They have a lot of memory. They're Google, but still, there are more efficient ways. So sometimes you need to consider that also. A matrix of adjacency, on the other hand, it gives you constant time for the answer, is there a path from A to B, from vertex 5 to vertex 3, but it uses too much memory. So as you see, you will generally need to do the compromise between memory and speed. In the graph case, well, you generally make a compromise of speed, because you can't have that much memory. Graphs are pretty large, and you can't store adjacency matrices for graphs, except in some very strange circumstances. But generally, you will need something else. For example, a list of neighbors. Okay. Polynomial algorithms. I told you that this thing over here, if we have this coordinate system, and this is the function logarithm of n, this thing is somehow bounded. It can't go larger than this asymptote. What's an asymptote? You don't care too much. But this thing stops growing, basically. It still grows, but it grows very, very slow. This thing is a polynomial time algorithm. If an algorithm has polynomial time, that means that it stops growing at some point. It still grows, but it really doesn't matter because you have really large numbers. And it grows by, for example, 1. Logarithm of n grows with 1 for 1 millionth element or something like that. Okay, so when you have polynomial complexity, you're okay, because if you have a lot of data, the number of operations will start climbing slower and slower. If you have non-polynomial time, like this thing is called exponential. We already spoke about it. The larger your numbers become, the faster the operations grow. So, if you have a large data set, a large amount of numbers, you should avoid polynomial algorithms. How do you do that? Well, that's a complex subject. Not all algorithms have effective optimizations, meaning that there are problems which require polynomial time, but they're very rare. Okay. Calculating time and memory complexity. Well, actually, we already spoke about that. Why am I going back? Okay. What you need to remember from here. This is actually the proof of what I spoke to you earlier about. You try to find an algorithm which does this stuff. N, or 2 times n, or n at the power of 3, or n multiplied by a logarithm multiplied by something else. That's okay, because it stops growing. It grows, but it doesn't start growing faster. This thing over here is like a balloon. The larger it becomes, the larger it grows. Basically, the faster, you could consider it like, don't know, a gas pedal. The more you press on it, the faster your car will go. No, that's not very true. Okay. Actually, the gas pedal is more like this. Okay. I won't make these analogies anymore. What you need to remember. Polynomial time means the amount of the data set doesn't actually affect your growth speed, the growth of your operations. Non-polynomial time, however, in that, the data stream, the size of the data stream, effectively changes and makes your operations count grow faster and faster. The larger the number you have, the faster your operations will grow, and the more operations you have to do. Okay. Let's take a break because you will fall asleep at any moment. 10 minutes from... Okay, so continuing with some examples. Doing this stuff depends on not that much on maths, etc. You won't need them that much. It's good to know how to calculate it, but it's not imperative. You could go through calculating the basics of the basic algorithm complexity of your program without knowing too much maths. There are relatively simple rules you can follow. For example, one rule is if you have all of your operations in 2 loops, 2 nested loops, for I from 0 to n, and for j from 0 to m, then your complexity is n multiplied by m, and stuff like that. So, what my advice is, don't try to learn how or what this means, or what this means, unless you're attending some special course in your university or whatever, or unless you're not a genius, a man who wants to suffer. I'm not sure of the word in English. So, yeah, you could learn these things. They could be valuable, but in the general case, if you've learned them, did I start my recording? Yes. If you've learned them, you will forget them. Most people that learn these things forget them. Learn the basics of determining how fast your algorithm will run. And here are these basics. Finding an element in an array. Complexity. We have n elements, or length elements. So this is the number of elements. Looking for the smallest element in those elements. Well, this is a linear operation. Why? Well, because we do something linear for all the elements in that array. Why do we say that we do something linear? Well, we say, if this thing is larger than something, and not larger than all of the other elements, but just larger than something, and this something is at the beginning the first element. This is a linear operation. Yeah, it takes 2 or 3 steps, but it's still linear. It does, for each element, it does this is one thing, 2 things. So yeah, this is 2 times some operation on n elements. Two operations on n elements. It depends on how you interpret it. So this is you could say this is 2 times n, because you first do this and then you do this. But as we said, we don't care about 2 times or 1.5 times or 2 times divided by 3 or something like that. We care about n only. So this is exactly n operations. Why? Well, because we go through each and every element of this array. N elements, length elements. This is basically big O notation of array dot length. That's basically your complexity in this case, in finding a maximum element. And from now on, you will just remember that finding the maximum element should be done in linear time. Linear time, because we only do something for each of the elements. Okay. This does linear time, and it does about n operations. This thing we call a basic operation. One basic operation, because it's in our for loop. This is our for loop, which does all the work, and this thing does processing of each and every individual element. Okay. So steps n. For each element, do something. Okay, find inversions. First, I had trouble of trying to guess what this means. This means if you have an array and you have 1, 2, 3, 4, 6, 5, 7, this thing is an inversion. 5 shouldn't be before 6, but it is, so this thing is called an inversion. These things are inverted. And also, if you have, for example, 1, 2, 3, 4, give me a number, 7, then 6, then 5, this thing is also an inversion. And this thing is also an inversion. And this thing is also an inversion. So we have a lot of inversions here. So how do you calculate the inversions? Well, for each of the elements, you go through the elements after it. What did we do here? We did for the elements 1, 2, 3, 4, 7, 6, 5. What did we do? We started from 7 and we went after 7 and saw, oh, 6. This is bad, it shouldn't be here. Then, oh, 5, this is bad, it shouldn't be here. Then, for 6, we did, oh, 5, it shouldn't be here. And that's it. 3 inversions. So, for each element, go through the elements after that, and wherever you find something smaller than the other thing, or something that ruins your sort, or whatever you call it, you increase the number of inversions. So, how do you calculate that? Well, it's a bit complicated, not that much. For example, you start with the outer loop. What it does? Well, it does I from 0 to n, right? That's n elements. Inside you have j, which starts from I plus 1 and goes to n again. If you write this down, if you write this through, you see that you have actually first 0, then 1, then 2, then 3, 4, 5, 6, etc. Actually, it's the other way around. It's not this. First, when I is 0, what do? Well, you start from n minus 1, then n minus 2, then n minus 3. When I is 0, you have n elements. When I is 1, you have n minus 1 elements, which are traversed with j. Then n minus 2, then n minus 3, etc., etc., etc. If you sum these up, you have an average of an increasing sequence. The average of an increasing sequence is what? If you have the middle value multiplied by the number of elements, the mean of all the values multiplied by the number of values. How do you calculate the sum of the numbers from 1 to 100? Well, you do 1 plus 100 multiplied by 100. And that's 55 or something like that. Multiplied by 100, that gives you 5,050. It's not 55, it's 50.5. 100 divided by 2 is 50.5, multiplied by the number of elements, which are 100, from 1 to 100. That's 5,050, right? Okay, so this thing does the same. N plus n minus 1 plus n minus 2 plus n minus 3. If n is 100, you have 100 plus, 99 plus 98 plus 97, etc., etc., etc. That's how you can calculate the complexity of this algorithm. And this thing, it runs in n at the power of 2 time. That's the size of the array at the power of 2, because for each element you do something with the other elements. That's generally n at the power of 2. With each element, do something with the other elements. That's n at the power of 2. And the number of steps you do, this thing is different. The number of steps you do is this, the mathematical formula for the sum of an increasing sequence. Because you have n plus n minus 1 plus n minus 2, etc., etc., etc. That's actually a decreasing sequence. It doesn't matter. You can turn it around. So, why is this n at the power of 2? Well, we said that when we write the big O notation, we don't care about constants. So, we actually don't care about this, and don't care about this. And what we're left with is n multiplied by n. And that's exactly n at the power of 2. If we want to be more specific, the exact number of steps is this thing. N multiplied by n plus 1 divided by 2. Why? Well, you should see the formula for calculating the sum of an increasing sequence. That's not that complicated. What you will care for the most is this thing. O of n at the power of 2. Why? Well, because for each element, do something with the other elements. That's n at the power of 2. If it was for each element, do something with each element, and with that element do something with another element, that would be n at the power of 3. The number of nested loops you have here, if that's your entire program, that's the complexity of your algorithm. Okay, enough about that. Something else. What do we have here? You have 3 for loops, what I told you earlier. Starting from 0, another one starting again from 0, and another one again from 0. That means that, yeah, that means cubic, you mean. You mean cubic. You mean that n, we have one n, another n, and another n. N multiplied by n multiplied by n. That's n at the power of 3. And the number of steps in this case is exactly n at the power of 3. We don't do any fancy stuff here. If there was b is a plus 1 and c is b plus 1, then it would be something like the last example. Not exactly, but something like it. So basically, you see to where your loops go. if they go from 0 or something relatively close to 0 to n, well, you multiply n by n by n. And that's n at the power of 3. Or in this case over here, n at the power of 2. Okay. Basically, you should try to either learn this stuff, either get used to it, or solve problems with it. There are a lot of complexity calculation problems out there in the internet. You could check some of these out, but this is the stuff you'll most commonly come into. Either this or this. Or for example this. What's this? This is complexity of how many variables? We have one variable and another variable, so it's two variables. Right here we had only one variable, right? Our entire algorithm is based on just one variable, and this variable is n. Here we have two variables. If we have two variables, we will most likely have complexity dependent on both of them. Like in this case, we have x from 0 to n, and then y from 0 to n. What complexity is that? Yes, n multiplied by m. And that's exactly the number of steps, because we don't have any fancy stuff going on around here. If we had y is x plus 1, then we would have the same thing like the first example. Not the same thing, but something like it. Okay. This again, how many variables? Again, two. Two variables over here. How do we use them? Well, again, x is from 0, this goes to m, and some fancy stuff around here. So, if x is y, then do some bullshit. And don't know what that is exactly. This is some weird way to multiply numbers. We don't care how much about that. What's the complexity of this thing? N by m by this. We have another n. So n by m, yeah, I lied. This is only if they're equal. So this is n by m, and if they're equal, do something else. But if they're equal, happens rarely. And when it happens, we don't care about plus something. That's why, here's what we have. A minimum of these things plus this thing. So here is n plus m, n by m, n multiplied by m. And then when this thing happens, we add an additional operation, go from 0 to n and do some other stuff. But this thing is relatively small. This thing is relatively small compared to n multiplied by m. And that's why we have only n multiplied by m. Because this addition, actually, what we have here is minimum of m plus n, m and n, right? And you say, well, what the fuck? We have n multiplied by m here, and this could also be n multiplied by m, right? And why aren't we adding that? Well, because this thing, when you sum n multiplied by m with n multiplied by m, you get what? 2 times n multiplied by m. And we said we don't care about 2 times. Big deal. 2 million or 1 million, it's still a million. And that's why our complexity is n by m. The total complexity, the asymptotic complexity, or whatever they call it, is n multiplied by m. This is what matters when these things become large. And you only care when these things become large. You don't care if they're 2 or 3. Yeah, your processor won't make the difference between 5 operations and 10 operations. When these things become large, they matter the most. This thing, if it's 2 times this, it doesn't matter. If it's 10 times this, it matters but a little. If these things are very large, it doesn't matter at all. Because 10 times is some constant. All constants go away from this asymptotic notation. Big O notation. No constants over here. And you should not care about these constants over here when you're writing your programs. Unless you're making games. That's something to remind here. Unless you're making games. If you're making games, 0.5 matters here, or 1.1 matters here. But In serious applications, in real-world applications, 1.3 doesn't matter here as a constant. In games it does matter because they were fighting for frames per second, but here it doesn't matter. It's not important. Okay, some other calculation stuff. This thing, can you guess how fast it grows?
Is it exponential?
Yeah, that's exponential, because we do something with this n, and what do? We use it as a power. This means shift 1 n positions at that way, which means multiply it by 2 at the power of n. And 2 at the power of n, as we said, is something which screws you up. So, this thing runs in exponential time, and the larger n becomes, the more and more operations you have to do. The number of increase in operations you have to do will be larger than in linear cases and quadratic cases. So you try to stay away from exponential stuff. Exponential stuff, something exponential, the nuclear explosion is exponential. That's exponential. Of course it weighs down in power really fast, but it's exponential. Because for each element that's destroyed, another n elements appear. Okay, that's not that important. That's exponential destruction, and that's what could happen to you if you use this kind of complexity, exponential destruction of your CPU. Okay, so factorial. How fast is this? What? It's not exponential, actually. This is linear. You just multiply by the last thing. You just multiply by something you generate next. You don't have a lot of operations here. You just say multiply by the last n. It's not exponential. This thing is not exponential. This thing is like go from 1 to n and multiply. It's the same, even though it's recursion. And recursion is cursed, basically. That's why it's called recursion, because it's cursed. So this thing ain't exponential. This thing is linear, because what it does is calculate this, then calculate the next one, then calculate the next one, then calculate the next one. It doesn't. Exponential means basically something like this: calculate this one and this one, and for these calculate this one and this one. And this one 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 and this one. That's exponential. Yeah, the Fibonacci sequence. Speaking about it, this thing is exponential. Because why? Well, because here we just have calculate one thing. But in the Fibonacci sequence, we have calculate those two things. For each one of these two things, we have to calculate two more things, because this will call another thing. And this will call one more thing. And these things will call other things. Etc, etc, etc. And this thing is exactly 2 at the power of n, depending on our n. The larger our n is, the more leaves we'll have here. These things are leaves. You know what a tree is. This is a tree. And the larger n is, the larger number of leaves we'll have here. These things will be a lot, if n is a large number. And they will be even higher for an even higher number. Okay, so this thing, you can imagine how it grows. Trees don't grow that fast, normal trees. I mean trees like in nature. They don't grow that fast. But trees of recursion grow that fast. And that's why recursion is cursed. And when you can avoid it, avoid it. So this thing grows exponentially. How do you avoid that? Well, you keep an array. And in the array, you store your answers. And that's dynamic programming, which you had on your exam. So, how do you optimize this? Well, you say this element here is this element, which I've stored already, plus this element, which I've stored already. And you call your recursion for these ones. You already have the answers for them. And just get the answers and sum them up here. Okay, so this thing is exactly exponential, and it works very, very slow. And if you have a large number, for example 15, this thing will probably crash your computer. That's 2 at the power of 15. Okay, 2 at the power of 15 won't crash your computer, but still a lot. It's 32,000 or something like that. Okay, so don't do this. Don't call recursion for something which divides itself into 2 pieces, unless you really have to. If you really have to do it, that's how you get exponential growth. Exponential growth is generally achieved by recursion. There are other ways. Okay, let's compare some data structures. We've already spoken about what data structures are best for what. Now we'll remind them and now hear your answers also. Okay, arrays. You already know what they are good at. You can get an element from its position. You can set an element by its position, get by its index, etc., etc., etc. Adding an element, deleting an element, and finding an element is slow. Why? Well, because if you want to delete an element, you have to shift all of the other elements in its direction. Meaning that if you have an array like this, and this is an element, and you have to remove this element, this thing has to go. What's the complexity of this? You have to move all of these elements back, right? With one position. And you say, whoa, but this ain't all of the elements, this half of the elements. Yeah, that's 0.5, for example, multiplied by n, or 0.3 or something like that. Whatever this part is. Yeah, but we said that we don't care about this. We only care about n. Because we could be deleting the first element. We could be deleting this. Then we shift everything. So, basically we have n multiplied by 0.5, for example, steps, and the total complexity is just n, because we don't care about the 0.5 part. Okay, linked lists. Deleting elements, and this thing isn't really true. This thing is true if it's delete by index. So, first about adding. How do you add an element? Well, you just put it at the beginning or at the end. That's fast. You know where the beginning and the end is. Okay, finding an element. Well, you have to go through all of the elements, just as in the array, because you don't have any special way of locating. Deleting an element. How do you delete an element from a linked list? This is a linked list with some elements in it. This is connected with this, and with this. How do you delete this element? What do you do? Well, you say that this thing goes over here. And this connection doesn't exist anymore. That's constant time. And this thing, which you saw here, isn't true. That's if you know which element you're deleting. If you don't know which element you're deleting and you have to find it, then you have this time. Why? Well, because you have to find it. If you didn't have to find it, it's O of 1. So this thing, if you don't have to find it, this is O of 1. If you already know where it is. But if you have to find it, well, it's basically O of n plus O of 1. And that's why the total is O of n. If you have to find it again. Getting by index, same thing. You have to go through all of the elements so you can reach that index. You have to count. Okay, this one is the first, this one is the second, third, etc., etc., etc. Okay. Resizable arrays or lists in C#. Well, what do? Same thing as arrays, only resizing is a bit faster, but not much faster. Basically, for a resizable array, your time in which you add elements should be constant in the general case. Because adding elements, you always have an additional capacity. And sometimes you have changes in your array size, but that's rare. And that's why you have constant time, because you always added the last position, and you're almost guaranteed to always have a last position. You will have a little number of generating new memory and shifting to that memory. Okay. Yeah. Basically, it's logarithmic if you consider the placing at another. Yeah. If you consider going from here to here, resizing your array, resizing is actually logarithmic, or it depends actually on the list type. If it's a C# list, yeah, it's exactly logarithmic. If it's not a C# list, it could be logarithm of with base 10 of something, or with base Nepper's number or something like that. Okay, so yeah, this thing resizing from here to here is logarithmic because it happens at exactly logarithm of n, exactly a logarithm of n number of times. But generally, adding a number is constant. You shouldn't care too much about this. So it's not really logarithmic time is not really very different from constant time. It is different, but it's very little different. Because what's the largest amount of memory you can have in your computer? Well, a logarithm of your largest amount of memory you can have in your computer is what? 100, 200, something like that. And the difference of one operation and 200 operations for your computer isn't that much. It's still a lot, but it's not that much. Okay. It's still better than the array. Okay. Stacks. Stacks, you know what stacks do. They can only add and delete elements, and they do it generally in constant time. Again, it depends on implementation, but they generally do it in constant time. Queues, the same thing. There's no real difference. Okay. More importantly, hash tables, dictionaries, tree-based dictionaries, hash sets, and sorted sets. Okay, what's that? A hash table, we already said, some sort of data structure in which we have a fast way of accessing elements by their key. Meaning that finding elements and adding elements and deleting elements is generally done in constant time. Unless you have to resize the hash table, but that happens very rarely. So, adding, finding, deleting, all of this happens in constant time. It doesn't matter how many elements you have, it only matters how fast you can compute your hash code of your key. It only depends on your key. And depending on your key means a constant time. Okay. Getting by index, you can't do that. Or at least you shouldn't be able to do that. You could implement your getting by index, but it won't give you anything real. Okay. So getting by index is actually O of 1, but you shouldn't be able to do that. There's no logic in doing that. Okay. So adding, finding, deleting, we said constant time. Tree-based dictionaries, we said that they use balanced trees. Balanced trees work with logarithm of n always. So basically, everything is logarithm of n with them. Adding elements, deleting elements, finding elements, it's always logarithm of n. And when you're searching for a sorted data structure, which is fast, you use a balanced tree. It doesn't matter whether you use a dictionary or a set. The only difference is that for a set you only have elements, and for a dictionary you have keys also. So if you need sorted data types with keys, you use dictionaries. If you just need a sorted list, you use a set, a sorted set. Okay, hash table based sets. What do hash table based sets do? Well, they're very good at finding elements again by their hash code. So basically, if you want to make intersections or joins or stuff like that, you should use a hash set because it's generally faster. Because it gives you constant time for searching for an element. Okay, you could use this table as a reference if you ever need something like that on your exam also. But you should probably view these things when you see them. A hash table, okay, why is it a hash table? Because it calculates hash codes. That means it doesn't care about the number of elements it stores. What's this? A tree. A tree cares about how many elements it has, because the more elements it has, the larger it becomes. That means it works slower than the hash table, but it's still fast. Why? Well, because it's a binary tree. And binary trees do almost everything in logarithm of n time. These two things are exactly the same. They just use less data. Okay, so when do you use arrays? Well, each time you need elements in some order by index. In order by index, only that. For example, if you want the square roots of the numbers from 1 to 100, that's a good example of using arrays. Because for each index means a number from 1 to 100, and each element at that index means the square root, for example. Lists, when you don't know how much thing you have to add. You have to add elements until he inputs a dot. And then you need to access those elements fast. If you don't need to access these elements fast, you use a linked list. And if you have to delete elements often. And this thing is not fully true. Linked lists are generally used if you have to always traverse your list. If you have to, for example, you have a number of things which can live and die. And you have some elements in an array. And these elements live and die. Some classes, for example, people. People live and die. And this thing lives, and this thing lives, and this thing lives, and this thing dies. Okay, when this thing dies, what do you have to do? Well, all of the living stuff after it has to be shifted back with one element. This thing goes here, and here, and here, etc. Okay. When do you use a linked list? Well, exactly in this situation, because you always have to go through all of the elements and check, has this one died? Like when you're checking hamsters, for example, in glass boxes, you go through all of the boxes and you see, oh, this one died. Okay, shift everyone. When you have to do that, you shouldn't use a dictionary, because, okay, if things die, it's okay, you have empty boxes. But if new things appear, you have to buy new boxes, and you have to reorder the boxes again. So when you have creation of things and death of things, you use a linked list. Why? Well, because you have to go through all of the elements either way. And for each element, you always check if it's dead, or if it's alive, or if it has given birth to something. And for example, you go, this is a linked list, and you start from here, and you say, okay, this one's alive, whoops, this one died, okay. Reroute this stuff, connect this with this, it's all okay. Then we're going, this one, oh, this one made a baby, okay, add a new element, connect this to this, and this to this, and remove this connection. And that's how you operate with the linked list. That's how you make games. In games, you have a lot of things which die, and a lot of things which are born. And you always go through all of the list, because you have to update all of the elements, right? You have to move all your cars, for example. And when a car explodes, what do? Well, you just delete it from that list, because you've reached it anyway, and your deletion is fast in that case. Delete it from that list, and connect the elements which are its neighbors. When a new car appears, someone buys a car, you just add it at some random position in the list. Okay, whoops, not what I meant to do. So, linked lists, when you have such situations in which you have to always check your elements. If you have to always check your elements, use linked lists. If you don't have to always check your elements, you have to check them from time to time, use normal lists. Okay, stacks, well, you know what to use stacks for, for cleaning dishes, for example. Or implementing some type of last in, first out. Queues, first in, first out, not really a matter of discussion what you do with these things. With this you do a DFS, and with this you do a BFS. And with a priority queue, if anyone's heard of that thing, you do Dijkstra. But that's not a matter of discussion right now, and I won't fill up your heads with nonsense. Okay, hash tables, and not that Dijkstra is nonsense, it's actually a very good algorithm, but you don't need it right now. But just remember that if you need Dijkstra, you use a priority queue or something else, but priority queues work fine. Okay, hash tables, well, when you need to access by key, when you need to translate words fast. You get a word and you need its translation into Swahili, for example. Well, you keep a dictionary with English keys and Swahili values and you're all set. Okay, and these things don't have any order. You can't get them ordered. If you want them ordered, not pretty sure why you would want them ordered, but if you do want them ordered, you use a sorted dictionary, which is a binary tree. And it always works in logarithm of n time, for everything. Only constructing the tree is n multiplied by logarithm of n. But that's not that important. Actually, it is important. Why is constructing a tree? Constructing a tree takes this amount of time, n multiplied by logarithm of n. Why does it take that time? Anyone, any ideas?
Because we have n branches that are equal of n.
Yeah, basically because we have our add operation works in what time? Logarithm of n, right? So constructing a tree, an entire tree from an array, you have an array of n elements, means what? Go through each of the elements and add it to our tree. That's exactly for each element, do adding. For each element, do logarithm of n. Each element means n multiplied by this thing. So that's why constructing a tree takes n multiplied by logarithm of n time. Okay. So if you need sorted sets or sorted dictionaries, trees. Basically, the sorted set and the sorted dictionary classes use exactly these trees. Okay, you've heard this stuff a lot of times. Basically, that's the basis of what you should know about calculating algorithm complexity whenever we're referring to time and to memory. So, time and memory, same stuff. You just calculate the input data, you have some input data which is n, or other variables eventually, and you calculate how many operations you have to do with these n things. If you have to do for each and every element of those n things, another element related with the other thing, another operation related with the other things, then it's n multiplied by n, which is n at the power of 2. So this is quadratical. In the same way, when you have an adjacency table for a graph, for each element you have all of the other elements and the connections to them. And this thing is again n by n. Either way, you calculate on the base of your input data what output data you generate, or what number of operations you do with each and every element of that input data. Okay, so what you can do with that? Well, you can estimate how fast your code will generally run. You can compare to other algorithms, because you can't compare with speed. Speed for n, which is 10, generally what happens, if you write a good algorithm, which does some magic and is optimized, for small data inputs, it will work slower than the dumb algorithm. It will work, for example, twice slower for small data sets. Because, for example, you do sorting or something else, or constructing of trees and etc. And that takes time. But when the data sets become larger and larger, your algorithm, your smart algorithm, starts working faster and faster. Because it's prepared something which it uses to calculate faster. Okay. So, keep into account this stuff. These 3 slides. Which is used for what and how fast you could refer to this table. These are things you should know. And it's not something you have to learn by heart. It's something you can derive by yourself. It's something you can think of by yourself. It's not that complicated. So Try to think of them and try to imagine how they work. Okay, so the fastest add, find, delete structure, as we said, is the hash table, but it's not the most memory efficient because it takes up more space than it has elements stored. Generally, hash tables are used very often nowadays, but it doesn't mean that you have to use them for everything. Keep that into account, but don't use them every time. Sometimes there are things that are faster than them. Not exactly faster, but more optimized than them. Okay. That's about it about algorithm complexity. That's what you need to know. Not everything, really not everything, but that's what you need to know. So, any questions? It doesn't matter in what language. I'll act as a translator. Okay, anyone? Anyone? What?
You are acting as a dictionary.
Yes, I'm acting as a hash table dictionary.
Is there any if list is it has a faster add function and getting its functionary has same getting its function, so why should we use array not list? Because list takes up too much memory. Why should we use array instead of list? Again, the problem with memory versus speed. Because list resizes very fast, but it uses more memory. What you could do, list has in C#, list has a capacity property. If you change it, the list will take its values and put them into an array which is exactly as long as if you set the capacity to the number of elements. It will place itself exactly in a place where it has enough storage for all the elements and no more. But that's one operation more. And generally lists save more information. If you have 1025 elements, then you will have a capacity of 2048 when you create it. And then you will have to shift it down. And if you have very large amounts of data, for example, you have 2.5 gigabytes of information in your list, that list will be actually 4.8 gigabytes. And that's when you create it. And you will get out of memory exception. That's why you use arrays when you can, when you don't need lists. Okay, anything else? Okay, not for now. Okay, so bye-bye guys.